This statement here is one of the most basic problems in numerical analysis, and answering it is going to be our goal throughout this entire chapter of lectures. But the way I've phrased it is significant. If we take the equation we're given and set it equal to 0, then we can think of the left side as hopefully a function or possibly just a relation. And this is important since it lets us rephrase the question. If p is a function, then solve this equation is equivalent to find the x-intercepts or find the roots of this function. And this is an important twist since we already have a toolbox full of tools for working with functions. So before we jump into our method, I want to bring back one of those function-related tools from your first semester calculus class that's going to be essential to our first algorithm. The intermediate value theorem says that if we have a function that's continuous on a closed interval from a to b, and I look at the values of the function at each of those endpoints, then I can pick any value I like between those two functional values, and there has to be a value between a and b that the function maps to that value. Right now, to apply this to our question, suppose I have a continuous function like this one, and I can find 2 points, a and b, such that the function is negative at one endpoint and positive at the other endpoint. Then the intermediate value theorem says that the function has to take on every value between those two numbers. In particular, there has to be some value between a and b where the function equals 0. And that's the value that we're looking for. So how can we turn this into a practical algorithm? Right? I think the best way to illustrate the method is to look at an example, and then on the next slide, we'll see how to generalize this into some pseudocode. So the process goes like this. First, identify 2 points where the function is positive at one and negative at the other. Our function here is negative at 1 and positive at 8. So we'll start our process with that interval since the intermediate value theorem guarantees that there's going to be at least one root in there between 1 and 8 somewhere. Now the next step in the algorithm is to calculate the midpoint of our interval. Right? That's going to be 1 plus 8 divided by 2, which is 4.5. That's right here. So if you look at the graph, you'll see that the function is positive at that point. So what I'm going to do is I'm going to replace the original positive endpoint of the interval, the 8, with the midpoint. And I'm going to keep the negative endpoint the same. Right? Now see what happened here. This has given us a smaller interval that the intermediate value theorem still guarantees that there's a root in. Right? Now we repeat the process. The midpoint of this new interval, 1 plus 4.5 divided by 2 is 2.75. And since the function is negative, at that point, I'll replace the negative endpoint of that steps interval with that number, and I'll keep the positive one the same. So this gives us a third, even smaller interval that contains our root. So at this point, the process of calculating the endpoint, determining the sign of the function at that point, and defining a new, smaller interval based on that result just continues over and over again, with the midpoints here being our approximations. Right? You do this over and over again until you reach the required level of accuracy. So I've got the pseudocode to implement this algorithm. And I'm going to go into a lot of the technical aspects in more detail in the next lecture, but I do want to just go over this a little bit here so you can see what it's doing. Right, so on this first line, I set my stopping criterion. One thing you always want to be careful about in every algorithm we're going to talk about is making sure that there is some way for it to stop. Right? And the way I do that here is I've just set a maximum number of loops, maximum number of endpoints that maximum number of midpoints that we're going to generate. Then on this line, this is calculating the midpoint of the current interval. See, A and B are the left and right endpoints of the interval. And then I do another test. If f of that midpoint is actually literally 0, we have landed exactly on the root, then we're done. Right? There's no point going any further. Or if this value, that is it's half the width of the interval, if that is dropped below some tolerance level, then output the value of p and we're done. Otherwise, we do this test here, right? We look at the function at the left endpoint. You can do this with the right point as well. And I look at the function at my midpoint, and I multiply them together. Remember what I care about at this point. Do these two things have the same sign, in which case one of them replaces the other? Or do they have a different sign, in which case p is going to replace the other endpoint? Well, my test to see if they have the same sign is just to see if that product is less than 0. Right? Because if they have the same sign, either positive or negative, then their product will be positive. But if the product is negative, then they have to have different signs. Okay, so this is, we'll call this the same sign scenario. So if A and P are both giving me negative function values, then my midpoint replaces the right endpoint, B. Otherwise, this is the opposite sign option, and that midpoint replaces the left-hand endpoint. We increment the counter, so we know we've completed another circuit through this loop, and we go back to the top, and the whole thing repeats. In the end, we output that midpoint. That actually is a fairly brave statement right there, just outputting the endpoint. We'll talk about that more in the next lecture, so you see exactly what's going on there. So now that you've seen that pseudocode for a new method called the bisection method, right? Hopefully for kind of obvious reasons, right? We start with an interval and then we bisect it, and that gives us a new interval, and we bisect that, and so on and so on. I encourage you to get out your programming language of choice and actually try to implement that algorithm. Right? The computer science people, when you're taking algorithm classes, they always say you don't really understand an algorithm until you've actually written the code for it. And you're going to have a lot of opportunities to do that throughout this class as well. Now, in the next lecture, we're going to dig into some of the technicalities here. We're going to look some more at that pseudocode and talk about some of the specific choices that I made in there. And we're also going to talk about why that was kind of a brave thing to say right there at the end. Some of the algorithms that we're going to be talking about here, you can't be certain that they're going to give you an answer. Sometimes you'll get a sequence and it diverges. Right? Well, the bisection algorithm is nice in that it will always produce an answer. We're going to look at why that is in the next lecture, and we'll also talk some about how fast this algorithm converges.